how would this be defined? Well, I take the integral, say from t1 to t2, of f of gamma of t times d gamma dt, where gamma is a parameterization of the curve as a subset of the hyperbolic numbers. So literally, exactly the same definition that we made for complex. Just the difference, the wrinkle, is that this right here, right, is a hyperbolic multiplication. That's the difference. And that's all the difference in the world. See, because we can also say this using the same identifications that we did before. What do you think u plus jv times dx plus jdy, how's that going to work out? This is what? Integral of u dx plus v dy plus j times the integral of, where are we? U dy plus v dx. It's easier to, in some sense it's easier because you don't have there's a sign. The signs are more nuanced for complex, right? You got to keep track of which one's plus, which one's, everything's plus here. It's all roses, you know? If you like that sort of thing. So what do you guys think? Is Cauchy's theorem true here? What would Cauchy's theorem be?
Seems like you can integrate across a hyperbola.
Integrate across a hyperbola. No. What you're thinking about is much harder, and as far as I know, doesn't work. I've tried. Like the analog of residue theory. I don't know what, I don't have a good answer to that yet. But if we make this the boundary of a simply connected, closed, bounded region, like usual, yeah. Maybe a rectangle, how about that? What can I do? Cauchy's theorem should say that if this is hyperbolic differentiable with continuous derivatives, right? Then this integral should be what? Should be 0. Is it? How do we prove this?
Green's theorem.
Green's theorem, right. So we do integral. And how's that go? We do partial x of the y component minus partial y of the x component. That area integral plus j times the integral of r of partial x of the y component, which in this case is v, minus partial y of the x component, which in this case is u. This is what? Vx minus uy, Vx minus uy. I might have flipped things around. Is that right? Feels too similar.
I think it should be Vy on the right.
Did I flip them? I said the x derivative of the y component. Yeah. These. I said it, but I didn't pay attention to the details, right? So that's supposed to be a u, and that's supposed to be a v. It should involve both. So yeah, this is ux. That's vy. But these are what? These are both 0 because those are the hyperbolic Cauchy-Riemann equations. So yes, Cauchy's theorem is still true. The integral of a hyperbolic differentiable function over some simply connected region, the boundary. If it's hyperbolic on that whole region, then yeah, the integral around the edge has to be 0. And by the way, this is not just true for hyperbolic numbers. I've proved this for an arbitrary finite dimensional associative algebra. It still is true. It's still true. A lot of these things are still true in that case, but not everything. So anyway, I think that's a good place to stop. Like, it's surprisingly difficult to prove like the fundamental theorem of calculus part 1 You know that one where, like, if you differentiate an integral that goes with a variable bound, you get back the integrand. So that's still true for complex, and it's also still true for an arbitrary finite dimensional associative algebra. I think I assumed commutative for my proof there. But it's a surprisingly technical. It ends up being harder. But anyway, this is all in the primer that I wrote for A calculus. That I still haven't published somehow. I really should publish it. Let's talk about the solution to your test. We should do that. Let's see here. Get your test back first. I guess we could do that. It'll take me a second to warm this thing up. Why do I have so many? Oh, I scanned like 4 different things. All right.
Oh, sorry. My bad.
Never mind. Just wasn't designed for my
Mm-hmm.
What was the plus 10 for?
I guess it's early Christmas. I don't know. Let's see here.
Curve that somebody got a 170? That you? No?
Wait. No.
Yes, there was a 10-point curve. That is correct. Yes.
Somebody got a 170.
That doesn't necessarily mean that.
Or just curve here.
Ice curve 10. See here.
Like that.
It seemed right. Because if I curve by a different number, I'd have to think about adding the number.
You could have curved by like 50.
I could, but too mean. Okay, so I don't know what you guys do. I try to give a gift. And it's not.
If I was the only one arguing
It's
about
not
the point.
freely. It's not hard. Gah.
I think I lost 12 out of 10 points on that one.
Yeah, I think most people lost most points on problems 1 and 2. Direct calculation means
High score.
doesn't matter from the definition. So, like from the definition, the parameterization of the circle of radius r is r e to the I theta. So you take the conjugate of that, you get a plus and minus e to the I theta. They cancel, and it just leaves you the integral of theta, which gives you 2 pi ir squared, which I was hoping that you'd be able to check by applying Green's theorem. But instead of it being a check, you verified your wrong answer somehow. Several people. So, this one is a Weierstrass M-test question. So I see something like this, I look at it, I go, oh, that's a p equals 3. Because when you take the modulus of this, the modulus of I is 1. And so if I'm within, 1 unit, if I'm less than 1 unit away from the center here, I can dominate the series by p equals 3 series. So pretty standard. This was a trap, which some of you fell into. I intentionally made this go over where the principal logarithm is not defined. You must pay attention to that, otherwise you will be wrong. That was the whole point. Others of you are using residue there. I don't know what that means. It's not a closed curve. Residues are for closed curves, or at least for indented,
Conveniently equals 47.
Yeah. Problem 5 we worked in class. I have nothing to say about that really. Problem 6 somehow worked out to 47 again. I don't know how that happened, but
Oh, it's 10 off. How did that happen?
A lot of people way off on there, but anyway, so you just take the function, you write down what it means for it to have a 0 of order 14, and then cube that thing, multiply by z minus z naught to the 5th, group all the powers of z minus z naught together, you get z to the 47 times this other thing, and that other thing is holomorphic at z naught with a cube, with the value which is non-zero, because we were given that the value of the the co-multiplant, whatever that thing is called, the h of z is non-zero. Problem 7, you know, this required a little bit of, I think some people divided and conquered, and so you didn't lose all of the points because you realized this is easy, I can do that part, woohoo! This part is not as easy. There are probably other ways to do it. The way I saw to do it was just to expand in terms of the power series for the cosine, and it's not a triple zero because it turns out that the sine squared has actually got a double zero. So you got a double zero over a cube, which means you actually got a simple zero, and it worked out to 9. I'm sorry, I forgot to divide by 2 pi I admit it. I was going to divide by 2 pi I there, and I forgot. It was almost 47, you know. I think this one I have talked a fair amount about already. I don't want to talk too much more about it. So look at that one. You know, here, if you got it wrong, it's probably because you didn't notice that this one's clockwise, this one's counterclockwise, and that matters. But it's also holomorphic between these, which means we can use the deformation theorem to say this integral is equal to that integral, whereas this integral is equal to minus that integral. So, oh, it worked out to 47 again. Interesting. And where was I? And then here, this was a homework problem, right? Which I split up into little pieces for you. You guys calculated the residue a better way than I did. I chose to use rule 4. I think I'm using rule 4 here. I should have written that down. My bad. But, you know, you guys just factored, which is great. Better, actually. Here, you really do need to draw the picture at some point. So some of you drew this picture in the previous problem, which was inappropriate because that's not the picture for the previous problem. It's a half circle. It's not the whole thing. But since you drew it back there, I gave you credit for it over here. But some of you are missing the picture. But still had most of it. I think most people had something here. It was good. This one is also apparently in the homework. And yeah. So it ends up being the factorial squared, I believe. So yeah, anyway, yep. This one, not much to say there. Pretty standard. And hey, this is what we just did in the hyperbolic numbers, so that seems like a good place to stop. But so what do you guys want to do Thursday?
Can we review?
Review.
No, that just means just get a school. No. Like, give like a good. Can't do that. Yes, you can. I totally.
Thursday you can ask